Okay, this is lesson 15 and we're starting a new unit. This is on, maybe might be called device physics. It mostly has to do with diodes and transistors and their operation and on using them. So we are going to deal a little bit with theory, but not a lot. Just a few fundamental aspects. And then much of all of the lessons will be constructing circuits and seeing how they behave. So this first lesson is on the behavior of diodes, and you may recognize a lot of the equipment and the different items when we look at the experiment, because it's going to be basically Ohm's law. So I think I even refer back to the lesson that was Ohm's law, where you found the resistance of a resistor, and you also plotted current and voltage for a light bulb. So you'll be doing sort of the same thing with a couple of differences. But first we have to look at a little bit of the theory of diodes. Well, this has to do with semiconductors. So you might think, well, a semiconductor is a sort of a conductor. It's not a really good conductor like the regular metals, like copper and silver. And it's not exactly a non-conductor like the other side of the periodic table. So they're kind of in the middle of the periodic table, which means that they kind of behave one way and kind of behave the other way, or they have characteristics of both. There are some semiconductors that are naturally semiconductors, but the ones that we're going to be using are what we call impurity semiconductors, and we'll see in a little bit why we want to use those. We have two basic concepts that we're going to talk about. One is electrons, which you're quite familiar with that. And then the other one is a hole, an H-O-L-E. So normally you think of a hole is a place where something is missing. And that's exactly the case here. So if we have an electron moving around, then obviously that's called an electron. But if an electron moves, then where it left could be considered a hole. And then if something moves into that position, then that hole is filled, and then it leaves a hole where it used to be. So that's kind of the idea of what we're going to look at. Now, on page 126, we're going to draw some things, and we're going to draw 9 silicon atoms. So if you're not familiar with some of these, you might want to go find a periodic table. I'll mention that. I didn't actually think about bringing one with me, but we also know, though, that silicon is right under carbon. You're probably more familiar with carbon. You know that it has 4 bonds. They are covalent bonds. We are going to draw them in a flat place on the board, but if you look at carbon bonds, they're called tetrahedral because the bonds go, and I'm not even going to try to show you, out in 4 different directions. So it's not flat, but it's very difficult to draw that, so we are going to draw them on our flat surface here. So we're going to draw silicon. We're going to draw 9 of them. So we have a 3 by 3. And the reason we do this is so that we can see what effect there is when we do these other things that we're going to do. So we're going to draw the bonds across here. get all of these bonds. So each of these bonds in the middle, it's it's a covalent bond. So it's one electron from this silicon and one electron from this silicon, and those go together to form a covalent bond. And then we just leave these sticking out here. They would bond to others, but all we need are these 9 here. So it just says draw 9 silicon atoms in a 3x3 arrangement and show the bonds for each atom. So that's what this is. Now, it says also then to draw a similar thing, except instead of this middle silicon, we're going to put phosphorus. So I'm going to draw that here. So we have 3 silicons. We have a silicon, a phosphorus, and a silicon. And then we have 3 more silicons. So we get a lot of these bonds in here. Okay, so that's all I'm going to draw at the moment. Now, if you look at phosphorus, phosphorus has a valence of 5. So I don't remember exactly. It has to be on the right side then of silicon in the periodic table. So in its outer shell, it has 5 electrons. Okay, so 4 of them can easily bond with, oh, I need some more bonds down here. 4 of them can easily bond with the electrons from the silicon, but that leaves 1 extra electron. So what does this poor little extra electron do? Well, we draw it here, and then it is bound loosely to this phosphorus. Because remember, these are not extra electrons. There's no extra positives or extra negatives. It's all neutral. But it's just that 4 of these bonded with the silicons, but it left this 1 extra electron, or 1 electron unbonded. So we normally draw it in an orbit there, and I think I'm actually going to change that. Since all of this is black, it's hard to tell what's what. So we're going to make the electron in red so it's easy to see. Okay? So that electron is loosely bound to the phosphorus. Now, what is actually done is a phosphorus atom is put into this silicon crystal. I don't remember exactly the ratio. There's not a lot of them. It's like 1 out of every 10 to the 5th or 6th silicons is replaced with a phosphorus. And how you get it replaced, that's a whole nother issue. Because these crystals have to be grown, and this is called doping. This is phosphorus doped silicon. And you can imagine it's not that easy to get the phosphorus atoms to go exactly where you want them. That's why, as we see a little bit later, a lot of the things that deal with the semiconductors, even if you have the same number on the diode or the transistor, they don't all behave exactly the same. They behave similarly, but maybe not exactly the same. So this is phosphorus doped silicon, and it has this electron that's reasonably free. So it is called an N-type, and you can think of it as N goes with negative for electron. It's also called a donor, and I think it's D-O-N-O-R, because it donates an electron. Okay? So then in step 2, we're going to do something similar. And I said to go ahead and draw a 3x3 silicon, so it looks just like we did before. And then what I'm going to do is I'm going to, instead of redrawing things, I'm just going to erase this and make the new one. So what we're going to do with this is to dope the silicon with boron. So if you look at boron, you'll notice that it has a valence of 3. It's in the first major row just to the left of carbon. So it has a valence of 3. So let's erase all of this. I'm going to erase this center. So now instead of phosphorus, which had a valence of 5, we're going to put boron, which has a valence of 3. So it can bond with 3 of these, but this fourth one over here, there's nothing to bond with this, so we have this vacancy, and I'll just draw it like this, and this is called a hole. Now, it does not have a charge, but in a lot of things and places in books, it's treated as a positive. Because if you have electrons moving one direction, if you have an electron from over here, and it moves and fills up the hole, then you have a hole over here. So you essentially have electrons moving one way and holes moving the other way, so they behave as positive charges. Now, they do not have a positive charge, but they behave as if they did have a positive charge. So we need to look at how we label these things. This is called a p-type, and you can think of it 2 ways. It's not an N, or as I was saying, that a hole behaves as a positive charge. You could think of P as positive. And then it doesn't donate anything, but it will accept an electron, so it's called an acceptor. A-C-C-E-P-T-O-R. So it's acceptor, not acceptor. Okay, now the other part that has to do with why and how all of this turns into a diode. I think in this section, let's see, I didn't, oh no, I do talk about this. Okay. So what we're going to look at is, why is all of this significant? And, you know, what's the big deal with it? Well, something that's a little more chemistry oriented, and I know a number of you have had a number of chemistry classes and are teaching chemistry. If you look at the valence band and the conduction band, which is the energy bands for conductors and insulators, and then the semiconductors, that will explain a lot of the energy levels for the various electrons and the holes. So I'm not going to go into any details about that, but if you're interested, you can probably look this up on the internet. I haven't looked. There's some modern physics books that talk quite a bit about it. And he does explain a fair amount in the textbook that you have. So after we figure out how to dope these different materials with the donor type and the acceptor type, then what we're going to do for a diode is we're going to put together 2 of these materials and see what happens at the junction. And so that's the important thing, is what happens when you have a donor type material and an acceptor type material, and normally we just call it N and P, so a PN junction. And an PN or NP is the same thing because you just have one of each. Now, later when we talk about transistors, we're going to look at PNP and NPN, but we won't do that just yet. Okay, so we're going to look at what happens when we have a junction with an N-type and a P-type material. And I'm going to draw this, let's see, a couple of other pieces of information, a forward bias and reverse bias. For some reason they call it bias, and it has to do with the positive voltage and the negative voltage. But in step 3 on page 127, it says to draw and label a circuit with a PN junction and show the effect of voltage for a forward bias and a reverse bias. Okay, so if we have a junction, and this is the material, so, well, maybe I won't put a solid line there. I'll just put a dotted line. And the other crucial thing is, how do you get those two pieces of material together? And how do you get it to stay together? You don't put glue. Actually, I'm not sure quite how you get them to stay together, but they're together. So what we have is, if this is a P-type material, and this is an N-type material. So remember, in the P-type material, we had holes. That was the one with the boron. So what we're going to do here is I'm going to draw several holes. Actually, I'm going to draw more than that. So, I have a lot more on my paper. I'm just going to do this. So we have somewhat evenly spaced, or somewhere between even and randomly spaced holes. And then over here we have electrons. So I use the convention that he has in the book. A solid dot is an electron, and then the circle is the hole. So now this is for the forward bias. And we're going to apply a voltage to each side of this, well, to the two ends of that. Oh, and normally we have a resistor. Sometimes it doesn't matter what size resistor we have, but if you have a voltage, and if you don't have a resistor, you can get a rather large amount of current, and then things get hot and burn things out. So we usually just put some kind of a resistor there. The alternative would be to, on this voltage, to apply only a very small voltage, but since in reality it's difficult to get batteries or our circuit board or anything to apply a very small voltage, like half a volt or millivolts, then we just go ahead and use what we have, and then we put a resistor there. So the thing is, if we have this battery, then it's going to produce an electric field in, or to the right. And we also know that this, the positive current, or the normal current, comes out the positive side of the battery. So up here, if we have an electric field to the right, then we need to draw arrows on our charges here to show which direction they're going to move. If you remember, the idea is that a positive charge will move in the direction of the electric field, and electrons move opposite. So here we're going to treat these as positive, so they will move to the right, and the electrons will move to the left. Put all the little arrows on here. So in this middle region here, when the electron and the hole meet, the electron fills the hole and then comes over to this side, so it can come on to this side, comes out here and goes through the battery and out the negative side of the battery. Remember, electrons travel the opposite direction as the conventional current. So with this arrangement, we have the electrons rather easily moving across this region, and we end up with an actual current. So the next step is to look at reverse bias, and I'm going to leave that one there and draw another picture over here. So I have our junction. I'm going to leave this as P and this is N. So we have the holes, we have the electrons, and then we're going to apply the battery, the potential difference, the other direction. So we'll have the positive side on the right. There's our resistor. Now, with that arrangement, that's going to produce an electric field the other direction. So our electric field is to the left. Now, what do our charges do in that case? Well, the holes go the direction a positive charge would go. So the holes move to the left, and the electrons move to the right. So if that's the case, the charges and the holes are moving away from the middle part, the junction there, and if they do that, there are no charges going to get across the junction to actually travel through the circuit to be current. So in this case, no current. Now, when you have an actual diode, it is possible, if you apply a large enough voltage, you can make a current, but then you have sort of messed up your diode. And that's called the breakdown voltage. And generally, I don't think we're doing anything that's anywhere near the breakdown voltage for what we're going to be doing. Okay, so then over here, I might put current. So in the forward bias arrangement, you will get a current. In the reverse bias, you will get no current. So that's the idea of how a diode works. Now, there's several different kinds of diodes. One is what's called a standard junction diode. Okay, let's see here. Okay, keep track of my pages. And then we're going to have an LED. You're familiar with that in calculators. It's a light emitting diode, so if the voltage is one thing, the light is on. If it's not, the light is off. And then we have another kind of strange diode called the Zener diode that we'll talk about in a minute. Not in much detail, but just a little bit. Okay, a few more things that we'll do on the board, and then we will go to the circuit and I'll show you some things. The circuit's really not that complicated, but there are a few things that I want to mention. So on page 128 at the top, I have a general circuit for any of these diodes. And then there's a couple of things that I need to mention, and then we're going to look at the circuits for the exact diodes and the arrangement on the circuit board as to what's connected to what. Okay, so the general arrangement is a diode. And I'm just going to put a little rectangular thing here for the diode. And we're going to have a resistor. And then up here we're going to look at current, so we need to put an ammeter in the circuit. And then I have a battery like this. Oh, I also over here have a voltmeter, because we want the voltage across the diode. Labeling some pluses and minuses on the ammeter and the voltmeter like this. Now, you notice that I haven't said anything about forward bias and reverse bias, but I wanted to show you the general idea for the circuit, and then we will look at exactly how you get the forward bias and the reverse bias on the circuit board. There's a couple of really nice ways to do it. Okay, let's put this as diode, and this is resistor. Okay, 2 or 3 things to note, and this is in step 2, that you really do need to actually kind of pay attention to this. I know sometimes it's pretty easy to, well, I did the other one all right, so I know how to do this, but there are a few slightly different things. The first one is that the orange DMM that you were using for measuring current or voltage, some various things, it should be set on the 20 volt scale, and you'll use that to measure voltage. Now, the other thing that we need to measure is current. And on the yellow meter, actually, maybe I won't say much about that just yet. I think I want to get all the circuits drawn up here, and then we'll look there. But for the yellow meter, we're going to use it slightly differently than we have before. Yeah, let me go ahead and draw the circuits up here so I can get everything done on the board that I want to do, and then then Adrian can refocus to our circuit board there. So on page 128, the standard junction diode. That's the little black diode, and it has a silver band on one end. And when we look at the actual circuits, I'll make sure that he gets a close-up of that so you can see for sure. So what you've done before, this is part 3. Part 3. Okay, we are going to use the positive voltage and the negative voltage. So we're going to have a circuit almost like that. So we have the ammeter there, and then we're going to go over here, and this is going to be connected to the minus voltage up in the upper right hand corner of the circuit board. And you may have used this before. This is actually the blue. So I'm going to put blue here. So we still have the plus side of the ammeter, the negative side of the ammeter, and then we're going to have our diode. And I would put a black line across here. It's almost the opposite of what you see, but I think it's better. This is the silver band. Silver band. It's across the end of the diode. Then we have a resistor here. And this is the 50 ohm power resistor, which I will show you in a minute. Because I did try this with some regular resistors and things get really hot. So I almost burned myself a few times and I felt heat, and I decided that's not really good. Okay, then we're going to connect to ground. So this is the black terminal called GND, also in the upper right hand corner. I decided not to draw this around up here. I kind of like it like that. And then we're going to put our voltmeter over here with the plus side there and the minus side there. Okay. So this is the forward bias. So actually what I'm going to do, I think, I would like to leave all three of these up here on the board. So what I would do is this would be the picture for the forward bias, or no, this is reverse bias because it's connected to the negative voltage. Yes, and I do have reverse bias on the left. Now, for forward bias, you should go ahead and redraw this exactly as it is. Leave the diode where it is. Don't turn it around. Don't turn anything else around. But for the, oh, I know how to do this. For this is reverse bias. And then what you're going to do is for the forward bias, I'm going to draw a line here and say you connect this to the positive voltage. So, and the positive voltage is yellow. Okay. So the general idea, since I don't really want to draw them all and be erasing a bunch of them, I want to draw them and leave them here. So what's in black goes with reverse bias, and that's connected to the negative terminal up in the top upper right hand corner. That gives you negative voltages. Then when you want forward bias, you simply move the wire from the negative voltage to the positive voltage, and that's the yellow terminal. Okay, you leave everything else the same. And that's one reason I did it this way, is so that you don't have to be moving these things around. Okay, so that's the circuit for part 3. And there is more that I want to say about that, but I want to get all the circuits up here. Okay, the next one is part 4. And basically what you're going to do is replace the diode with, or this is the standard diode, you're going to replace it with an LED. So the difference is, let's see, I need my ammeter and my minus voltage. We go over here. And the LED that I want you to use, you should have 2 of them. You should have a yellow one and a green one. And I don't know that it makes a lot of difference. You'll get slightly different values. But what I did was the green one. And I'm going to put green LED. Okay? So we have resistor here. Oh, resistor's up there. Same resistor, so you don't have to take anything out there. There's the ground. The voltmeter stays over here, plus and minus. Now you may need to take it off if you've connected it to the diode there. You'll need to take it off. If you've got this connected closer over here to where this ammeter is, then you might not have to remove it. But anyway. So now, the thing that you have to look at on the diode, on the LED, and I'll show you that, is the leads to this are slightly different length. There's one that's a little bit longer than the other. You may have to straighten them out, and most of these that I've sent are or have been used before, so they're not exactly straight, so you may need to straighten them out. And one lead is a little bit longer than the other one. So what you need is the short one up here and the long one down here. They're only maybe a couple of millimeters length difference, maybe only 1 millimeter length difference. Okay. So again, this is reverse. And then when you get the data for that one, then you will leave everything where it is, and you'll change this over to the positive, and this is the forward. Now, I guess if you have ended this one with the forward, you need, I don't know, I guess you could go ahead and use this one as forward and then go to reverse. It doesn't really matter whether you do the reverse first or the forward first. But I've talked about them as going from negative to positive. Okay, so that's how you connect that circuit. Then the last one that you do is the Zener diode, and that is part 5. So it behaves a little differently, and it looks a little different. So again, we have our ammeter, plus, minus. Over here is minus voltage. This is reverse. Go over here, down, we need a diode, down to our resistor, over to ground. This is R. We need our voltmeter over here. We have plus and minus. This is the Zener, Z-E-N-E-R. Now, the Zener diode is designed to operate differently than these. It's operated in what's called in reverse breakdown. So it does have a forward, but the forward bias doesn't start operating till a rather large voltage, and that's usually not what we want. So we're going to look at the Zener diode in reverse bias, and that's when it's going to do its thing. So, oh, here's my picture. It is the one that is mostly clear, kind of like clear glass. It's about the same size as the other diode, but clear glass, and it has a black band on one end. It's actually a longer region than the silver band. It looks like that it's not really a band painted on there. It looks like they made that out of black glass, and then this part is clear. Okay, so you'll have that circuit, and the whole idea is once you get this pretty much set up, when you go from one diode to the next, you simply take this one out, put the other one in, and maybe move this from forward back to the minus voltage. Let's see, I need to put this over here. Positive, this is forward. Okay, and there are places for you to draw the circuits, and I suppose if you wanted to, you could do this and just draw one circuit, but it would actually be better because I have a region there for you to draw the reverse and then the forward bias. Okay, so those are the circuits. Now, some other things that I'm going to talk about and maybe write a little bit more here, and then we'll look at the circuit board. Okay, let's see. Oh, a couple of important things. If you haven't figured out by now, you really need to read carefully instructions and do what it tells you to do. So on page 129, which is the first graph, and I know some of you did the other graphs like on Excel or plotted them on something else and then imported them, and that's perfectly fine. I don't really care. But there are two main things. Notice that this says to plot a graph of current versus voltage, and I even have in parentheses, not voltage versus current as you did before. And the reason is that we want to see what happens to the current when we change the voltage. So your graph is going to have current here and voltage here. So it's going to be current, and you should have units there and should have units there. Now the other thing is, you might already suspect, well, I'm not going to tell you too much. Well, if you've looked at the instructions, it tells you for these two, for the first two, that you should have the voltage going from -6 to 0 in increments of 2 volts. And then in the positive, you don't really do very much changing the voltage because some other things happen. So it tells you what voltages to use. So there might be a tendency to use a different scale in the negative region than in the positive region. And that you should not do. I didn't actually write it there. I didn't think about, I haven't actually posted these yet. I might add that. So what you want is -2, -4, -6, and then over here is 2. So I'm not sure, I don't remember exactly. You might need to go up to 4. But whatever scale you have, and you do need to have the -6 on there, whatever scale you have on the left side of the y-axis, you need to have the same scale on the right side. And the reason for that is that it emphasizes the effect of the diode. Otherwise, you get things that are kind of distorted, or they don't really convey what you're supposed to be seeing. Okay. And I guess the same thing on the current. Whatever you start with, continue that. Don't have any of these little breaks in here where you don't start the current until like maybe, I don't know. Just don't have any breaks in either of them, and have both scales continuous across. Now, you won't necessarily have the same scale for all 3 of the graphs. You probably should have the voltage scale the same. The Zener one will be a little bit different. But the main thing is, whatever scale you pick, use that for the whole axis, horizontally and vertically. Now, obviously, whatever scale you have for the horizontal axis, you don't want that necessarily for the vertical axis, so that wasn't what I meant. Okay. I think we're ready now to look at our circuit diagram, and I will tell you ahead of time that I have 3 circuits set up here, and I decided to just leave them. We'll only look at one at a time, but the middle one, this middle one right here is the one that we're going to use now. So I have my circuit board plugged in, and I'll go ahead and turn it on. I need a pointer. So what we want to do is start and go from ground. So we have the ground over here. It's the same ground that you've used before. It's not the one in the lower left-hand corner. That goes with the function generator, so we're not doing any of that. So we have the ground here. So you need kind of a longer wire. Now, since you probably won't have this, if you want to do it in the left region or in the right region, that's okay. It doesn't really matter which region you work in. So I have it kind of down here toward the bottom. And then this one is the 50 ohm power resistor. It's a rectangular block, I guess. It's a lot of ceramic, and it's designed to withstand a lot of heat. So that's why we have that one. The leads to it are a little bit bigger than the resistors and these other wires, so it's a little harder to get them in the holes. Just kind of be gentle, but you still have to push hard enough to get it fit into the hole. So I've got it in there and in here. Now this one, I think I'll bend it a little bit away like this. This one is the standard junction diode. It's black. It looks a lot like a resistor, but it doesn't have a bunch of the colored bands like a resistor does. It does have a little silver band on one end, and it also has a number. It's a 4001. And what happens with these, there are some that have different numbers, but the last digit has to do with the breakdown voltage. And I think I've managed to have everyone with the 4001, and that means a breakdown voltage of 50 volts, and we're not going to be anyways near close to that, so you don't have to worry about it. Okay, so I've got the diode in here. Make sure it's in the same row, and then up here. So you notice that, let's see, I have this, I'm going to leave it this way. I have this in the forward bias position because this wire is connected to the positive voltage. So if you want to do the negative first, so you would just move it over here to the negative voltage. Now, remember that these two terminals are changed with these two knobs. So you should have them all the way counterclockwise when you're not actually adjusting them. So they need to be turned down. Okay, so I have this in the positive, and this, my table moved. Okay, this is the positive one, so I will end up turning the voltage up by using this. Okay, notice that I don't have this in the circuit board because I want to measure current, and I want to measure current between the diode and the positive here, or the negative, whichever case it happens to be. So I've already disconnected that or broken the circuit here so I can insert my ammeter. And this yellow meter we're going to use as the ammeter. Now on page 128 under notes, there's a couple of things about this. In some of these you are going to have close to 200 milliamps or possibly a little bit more. And I know from experience that when it gets close to 200 milliamps, it can burn out the fuse in the meter, and you really don't want to do that. So the alternative is we have another hole over here to use for current that's called 10 amps, which is a lot. We don't get close to that. But the 10 amp hole is unfused. So there is not a fuse in there anywhere to protect that. So when we want to use this, we'll have it in the 10 amp hole, and then we go down to the 10 amp. There's just one setting for that. It's in the lower right hand corner. It says 10 amps. And it also has the A with the solid line. That means the DC current. So this is what we'll be using. Now, let's see. Let's go ahead and turn this on. I'll show you maybe one or two data points. So I need to connect this between the positive terminal here and the diode. So I can connect that there. And I do have it in forward bias arrangement. And notice I am getting a current. So that's good. Now, I have my voltmeter. Notice that the red needs to be in the volts and then black in the commons. And we're going to use 20 volts. So I've got this set at the 20 volts DC. So the DC is down here. Let me move this over a little bit. And we'll turn it on. And then we're going to connect the negative to the bottom side of the diode. And since the diode and this side of the resistor are in the same hole, you can connect it either place. And then this goes connected to the top side of the diode. So you'll notice that this says 0.7 volts. This is turned down, the positive is turned down as much as it'll go. So we turn this up a little bit and the voltage changes and we get more current. Now, these are amps, so it's like 0.03. And probably the best thing is to go ahead and record them, although I think I've got them in milliamps. No, I have them amps. When we were doing Ohm's Law, I had you recording in milliamps, but here I think I have all of them in amps. So you turn it up a little bit, and then that changes, and I tell you on each one of them what range of voltages to use. Now, it's possible that they may not behave exactly as the ones that I have, so if it looks like you need to go up a little bit higher voltage, that's okay, just not a lot, okay? So that's basically what we have for the diode. Now, I'm going to go ahead and turn this off and turn the meters off. And then I want to show you, let's see, get all these things undone here. The diode, the LED. So if you notice on this, and I don't know where's a good position. It needs to have a black background maybe, because up here it's hard to see, I think. So down here. I have the little green LED. You have a yellow one. I think the graph will be a little bit different for the yellow than the green one. So if you notice, this side is just a little bit longer than the other side. And up here, I have which side to put the short, in the circuit. I labeled the side to put the long one and the side to put the short one. And then the last one that we have is the Zener diode. So, as I said, it is clear, and then, that'll work too. I keep moving these things around. Here you can see that there is a black end, and this part's clear. Now if I move it down here, then you maybe can see the clear a little bit easier. But the simple thing is just take the junction diode out, put the LED in, take the LED out, and put the Zener diode in. Now, as I said, the Zener diode's a little bit different, and it tells you on there, though, what range of voltages to use for both the forward bias and the reverse bias. A few things that my husband, when he was teaching this, that he always said, if you smell smoke or see smoke, turn the circuit board off immediately and probably unplug it. And then call your instructor. So it might also be a good idea to kind of put your hand over these things, preferably not touching them because you could burn yourself if something's not working right. But again, if you have any questions or if you're not sure if things are behaving properly, it's a good idea to call me, and then I'll help you figure out if you have things wrong or how they should be.